Morning, guys. I know it's hot in here. If you're all right, you can. It's cooler. It's probably about 4 or 5 degrees cooler up front because I have these doors open. There's a pretty good draft. So if you want to move up, you can. If you're comfortable, that's fine. Um, we'll have the quiz at the end of class. Probably a little before that. I'll probably give you extra time at the end just because it is. Is it hot in here or is it? It is hot, right? Yes. Is that where you're from? South America. Really? Cool. Um, he's from Louisiana. Are you from Louisiana? Are you an immigrant? No. Okay. Um, you had a good weekend? No? Any big news from the weekend? We went to see the Hamlet play. Have any of y'all seen that? Or any of you involved in it? I don't know if you were actors, but it was really good. I thought it was a very nice production. Um, any other big news? Yeah, y'all just want to take the quiz, right? Yeah, I know. I want to review for a few minutes. I realized that some of you were, huh? Okay. I realized that, good, that was you. Yeah, we'll review for a few minutes. I realized that some of you are a little confused about the whole chapter. Okay. All right. Um, we're going to move on to chapter 8 next, and then on your syllabus. All right. I don't know what that was. We're going to move on to chapter 8. And then on your syllabus, it says that chapter 9 is TBD. I think we're just not going to do chapter 9 because we only really have a few more chapters left, right? And there are some topics that I feel like are important for y'all. So we'll skip some of chapter 9 and move on to later chapters. We really only have 4 more chapters left because we've been sort of doing 2 chapters per quiz, and today is your 3rd quiz. So you're 3/5 of the way done through this course. Right? Okay. So let's look at chapter 6. Now, chapter 6 had a number of different things in it. Pascal's principle, Bernoulli's principle, Archimedes' principle. I think, and then also the measurement of pressure. I think Archimedes' principle is probably the most difficult for some of you. And, you know, that's partially my fault. Some of the homework was probably more difficult than it needed to be. Yeah, some of the substitution got a little complicated. So, in short, let's consider, remember the video we watched about the lady that was being hydrostatically weighed? She was sitting on a scale. This is the scale. That scale measures a certain force, and so that measures her weight. And then let's say that the weight of this woman is 600 newtons. All right, that's her actual weight. She has a weight of 600 newtons, so roughly 60 kilograms, and a weight of 600 newtons. But then the force of the scale whale measures, because she's submerged within a tank of water, it measures more or less than 600. Amy, more or less? Less, right. So it measures less. Let's say it measures 400 newtons. All right. So why is it measuring less than her actual weight? Because, I mean, she's sitting on the scale, right? Why is it measuring less? Because she's submerged in water and there's a force acting upon her. That's the buoyant force. So we know that there has to be another force acting on her, and that force is the buoyant force. So there's another force that's pulling up on her, and that's the buoyant force. Anybody tell me what the value is in this case for the buoyant force? It's 200, right? Because I have 600 down, and I have to have 600 up. That's Newton's second law, that if it's an equilibrium, as this is, the upward forces have to equal the downward forces. And so this buoyant force has to equal 200 newtons. And so when you're being hydrostatically weighed, like this woman was in the video that we watched, that's all you're trying to measure is what is the difference between the actual weight and the weight that you measure submerged in water, and then that's going to be our buoyant force. Now, the buoyant force is equal to the weight of the displaced fluid, equals the weight of the displaced fluid. If you remember in the Bill Nye video, he took the boat and set it in water, and then he got all the water that was being displaced and put it in those beakers, and then he showed that the weight of those beakers was equal to the weight of the boat. That's Archimedes' principle, that if you displace a certain amount of water, that the buoyant force is equal to the weight of the displaced fluid. All right, a fluid, of course, being a gas or a liquid. So actually, there is a buoyant force acting on you right now because you're displacing a gas, right? But it's very small. Why is it very small? Let me write the expression for the buoyant force first. The buoyant force, this is on your equation sheet, it's the density of the fluid times the volume of the object. And collectively, these two give the mass. And then since we want the weight, we're going to multiply that times g. So that is the buoyant force. So we're in a fluid. We're displacing a certain amount of fluid, like each and every one of us right now is displacing a certain amount of fluid. So why is our buoyant force really small? Smaller than what we find in the water thing. Gas is what? Gas molecules are farther apart, so the what is really small. The density of gas particles is really small. Right? So the density of our gas molecules is really small, which gives us a very small buoyant force. All right, so let's say, for example, I wanted to figure out what is the volume of this lady, which is really what you want to know because you want to figure out what is the actual density of the person in this hydrostatic weighing, because from the density you can determine the muscle mass, fat mass, all that business. So I would just solve this for the volume. Divide both sides by the density and gravity. And so it's just going to be the buoyant force over the density of water times the acceleration due to gravity. That's 200 newtons divided by the density of water is 1,000 kilograms per cubic meter times 10 meters per second squared. So that's 200 over 10,000, 0.002. All right. I know it's hot. Yeah, hot. That's the volume of the displaced water, but that's also the volume of the person because the person is displacing that water. All right, it's very difficult to measure your volume, right? How in the heck are you going to measure your volume? You're going to get a ruler and measure the diameter of your arm and the circumference of your head. It's very difficult because we're very regularly shaped. But this gives us a very easy way to measure the displaced volume of a person. And if you know their volume, you can find their density because density is just mass over volume. And density is really what you want to get at. I understand. Yeah, Lindsay.
Okay, so if we have that kind of problem, like there's
And you will.
Mm-hmm. And then a scale, and then just a regular part, use that sometimes.
Right. But I want you to think more about it than just formulae, right? I mean, the buoyant force.
I just don't understand.
Oh. Okay. Right. The buoyant force isn't necessarily the weight of the object. Right? There are two scenarios when we have objects that are floating. When it's floating, the buoyant force equals the weight of the object. When it's completely submerged, it's not necessarily the weight of the object. In fact, here, the buoyant force is 200 newtons, but the weight of the object is 600 newtons. So it's something less than that. If you sink to the bottom, the buoyant force isn't enough to hold you up. Y'all do this if you have this problem? Yeah, the 1,000 is the density of water. It's on the table. And listen, guys, on the test, on the quiz, be careful because sometimes you need to use the density of water in grams per cubic centimeters, and sometimes you need to use it in kilograms per cubic meter. And the way to tell that is to look at the units, the other units of the things that are in your problem. And in some cases, I've actually put it in the problem just to sort of guide you in the right direction. But look at the other units, and if you see grams or centimeters or whatever in the other units of the problem, then that's what you'll need to use for the density, grams per cubic centimeter. If you see kilograms or meters, then you need to use kilograms per cubic meter. So be very careful on that. I try not to be misleading as much as possible. I mean, sometimes it just sort of comes up that way. Huh?
On your work in the homework, you said that we would have to convert hours like that.
Right.
So
Mm-hmm. I provided that for you.
It's all there already.
Mm-hmm. This is sort of what I've gotten the most questions about. I know that it's confusing. I'm sorry, some of the homework problems were a little more difficult than they needed to be. All right. This is really what I want you to be able to understand, that the buoyant force, whenever you're in a fluid, you feel this upward force on you. And you can find that upward force as the density of the fluid times the volume of the object times the acceleration due to gravity. Does that set you at ease a little bit? Uh-huh. It would be straightforward. Right, I found that thing. All right. For some other topics from this chapter, Bernoulli's principle. In short, Bernoulli's principle says that when the velocity increases, what happens to the pressure? Does the pressure, it decreases, right? So that allows for a number of things. Primarily, if you're in the medical field, it allows for the entrainment of fluids. Right? I went over several examples where this entrainment occurs, but basically you have this high velocity fluid that you're creating, like in the perfume atomizer, and that causes a low pressure, because when the velocity increases, the pressure decreases. Bless you. Low pressure causes to suck up that perfume, or in the Bunsen burner, sucks up the air, or in this liquid entrainment, like you have with respiratory therapists, it sucks in whatever medicines or fluids or whatever that they want to include in the airstream. All right? Bernoulli's principle says that when the velocity increases, the pressure decreases, and that's important for entrainment of fluids. In that chapter also was Pascal's principle, which says that when I have a pressure felt at any point in a fluid, that pressure is felt throughout that fluid. That's the key principle behind what type of system? What type? Hydraulic systems, right. Like in car lifts, brake systems, you'll probably see a problem like that. You just say that the pressure at one point equals the pressure at another point. We worked through a couple different examples in class, and you had homework as well. The pressure is force over area. I think y'all are probably okay with that, right? For the most part. The other was pressure at a depth, or using different measuring tools like a barometer or measuring blood pressure. And remember, like for example, with the blood pressure, when you're measuring blood pressure, you get it in millimeters of mercury, and that describes the height of the column. And you can convert that back into a real pressure, given that millimeters of mercury. P is equal to rho GH, the density of the object times the acceleration due to gravity times the height of the column. We worked through several problems like that as well. That was chapter 6, really. Pascal's, Archimedes, Bernoulli, and the pressure at a certain depth. I think that was all. I think it's probably easier than y'all think it is, I hope. Oh. Okay. Questions? 5 or 6? Which one? Can we not? Okay. Because I want to take that up. Because I think that I didn't do a great job picking the homework, but they were more complicated than they need to be. I think they are okay with these. Are you okay with this? Is that okay? You're not going to see stuff like that. I don't want to confuse y'all. It's hot there, is it not? Okay, what's up? I think, was that on the equation sheet? Number of pascals equal an atmosphere? No, I'll give it to you if it's not. I'm not sure that it's relevant for the test. But if it is, I'll give it to you. I'll have to take a look. All right. Let's go ahead and take our test. Is that okay? Now what is, it's miserable. Are y'all miserable? Just say yes. Okay. And then we'll pick up with chapter 8. Is that okay? I know y'all paid good money to be here. But all right. So I want no more than 2 people per row, please. So you have to spread out. You need a calculator. My freebies have already gone out, fortunately. So, but if you didn't bring a calculator, just let me know. And as soon as they're done, then I'll give it to you. So only 2 people per row, please. You can move to the outer edges if you like. Yeah, and you don't need to know the atmospheres thing. I don't think it's on the equation sheet, but you don't need to know it. Okay? Oh, it is on the equation sheet, actually. 1 atmosphere is 1 times 10 to the 5th. Oh, you need a Scantron and a calculator. No cell phones, please. It's cooler up front. All right, ready? You're welcome. This goes all the way over. Karen? You take one over to Adriana. Adriana, right? I know, but that's for Karen. Can you take one to Adriana, too? Okay. Done? Guys, if you have my, you need one. If you have my calculator, as soon as you're done, then please give it to me. Or is anybody